just barely started talking about friction at the end of class on Tuesday. And that is the last topic. Is that true? The last topic before the exam? I don't think that's quite true. Almost. But it's the last of the 3 contact forces. So we had pushing contact. So if something's pushing on the chosen object, is the force toward or away from the chosen object? Nicole? Oh. Why did you raise your hand right as I asked a question like that? Okay. Oh, no, the quiz. Okay, I'm behind grading. This is the last one that's getting canceled, but this one's canceled. Each one is worth more percent. I'm dropping a quiz. Yes. Yes. I'm going to get so much done tomorrow and this weekend. Right. That's right. And last weekend I didn't get anything done because of the break. Yes. Yeah. But they still are going to add up to 20%. But, I mean, you still get to drop one of the ones you take, you know? Oh. Well, I think them's the breaks. Okay, so what I was asking before is, so if something's pushing on the chosen object, does the force go towards the chosen object or away from the chosen object? Towards, good. And the second type is pulling. Does the force go away or towards the chosen object? Away. Yes. And then the last type is friction. We're done with these 2. And so now we're talking about friction. And friction force can be broken up into 2 categories. There's static friction. That's the force that's required to keep something at rest. And then there's kinetic friction. And that's the one that acts on a sliding object. So the object has to be moving. This is the one we're going to do, and we're going to skip static friction. So we're talking about kinetic friction. And friction is a force, so it's a vector, and that means, you know, any force has a direction and a magnitude. The direction is always opposite the velocity vector. And that sort of makes sense if you think about a force as trying to produce an acceleration. Friction is always trying to slow things down. You can't ever use friction to speed something up, you know. So friction is always trying to accelerate objects opposite the velocity vector. That's what it means to slow down, you know. And then the magnitude is this constant, the Greek letter mu, sub k for kinetic, times the normal force. Okay, so let's do some examples. So let's say there's a 10 kilogram object on a flat surface, and it has a force pushing it to the right of 30 newtons. And let's say that the object at this instant is sliding this direction. So that's the direction of motion, or the direction of the velocity vector. Okay, so first of all, the first question is, how is it possible? How is that possible? You know, because there are no forces there shown that would cause the motion in that direction. This is something that's going to come up in a lot of these problems, so I want to sort of clarify this. It looks a little weird, right? But the thing to remember is that the velocity doesn't depend on the forces happening at an instant. The velocity depends on the forces that happen before this instant, you know. And so what could have happened is a big force was applied in this direction, got this thing moving really fast that direction, and then right at this instant that force was removed and this force was applied. So this is totally possible because the velocity doesn't depend on this. It depends on what happened before that. Okay. It's like if you, so what's happening here is like, it's easier to imagine if it's ice or something that doesn't have a lot of friction. If this thing was sliding along the ice at 15 miles an hour, and then you tried to stop it, you know, there would be a brief period where it would be moving in this direction because you hadn't stopped it yet, but the only force would be opposite that. That's because getting it moving 15 miles an hour depended on the previous stuff, not on the force at that instant. Any questions about that? Okay, so let's start with a free body diagram. No, we don't know what that is yet. Oh, and but I do have to give let's say that the coefficient of friction is 0.2. So, you know, it makes sense that if we're trying to calculate the acceleration vector, it makes sense that you'd have to know what type of surfaces these are. If they're both made out of sandpaper, the friction is going to slow it down really, really fast. If it's steel, smooth steel sliding on ice, that friction isn't going to have much of an effect, you know. So we have to know something about that interface. So in the free body diagram, there's the weight force, 10 times 9.81. And then there's pushing force of 30. And then there's the pushing force from the surface up to the object. We don't know what that is, so I'll call it N. And then the last thing is the friction force. Do we know what direction that's going to go? It's going to go the right. Yep, it has to be opposite the direction of motion. So I'll draw this over here. And the magnitude we know is going to be 0.2 times N. So I'll just put it in like that. And now Newton's second law says 0, negative 98.1. Plus 30, 0, plus 0n, plus 0.2n, 0, is equal to the mass times the acceleration vector. Is this thing able to move parallel to the x-axis or the y-axis? X, and so I'm going to write the acceleration like this. And we don't know yet whether that acceleration is going to be positive or negative. Well, I mean, I guess, let's say we don't know. It doesn't matter. You don't have to guess about the sign. You can just always write an A in either the X or Y, depending on which way it's free to move. And the plus minus sign will work out for itself in the math. Okay. Notice that one thing that's changed, like if you were doing a problem like this with no friction, you could just skip the y equation that says negative 98.1 plus n is equal to 0, because that doesn't give you anything that helps, you know. But that changes now with friction because we need to calculate n and plug it in here before we can calculate a. So we're always going to solve the y equation to find n and then plug it into the x equation. Okay, that's just every problem, that's how you're going to do it. So the y equation says negative 98.1 plus n is equal to 0. So n is equal to 98.1. And then plug that into the x equation, and you get 30 plus 0.2 times 98.1 is equal to 10a. And so 30 plus, I think that's 19.62, is equal to 10a. So 49.62 is equal to 10a. And so a is equal to 4.962 meters per second squared. That's not the acceleration vector, that's just a value for the variable a. So now we take this and plug it back into the expression that we already came up with here for the acceleration vector. So you can always take those variable values and plug them back into something in Newton's second law to get the final vector answer. So in this case, the acceleration vector is equal to 4.962. Or in other words, that's in the positive x direction, so you could also think of it as the acceleration is like this with a magnitude of 4.962. So is this object speeding up or slowing down? Slowing down because the direction of motion is to the left and the acceleration is to the right. So just sort of connecting this to the stuff we talk about in lab. You know, in lab we talk about the acceleration as a parallel part of the acceleration and a perpendicular part. Is this the parallel or perpendicular part? This is the parallel part. What happened to is there any perpendicular part? No, because at this instant the object's not turning. It's moving along a straight line. So now let's do this problem again, but I'm going to add one more force to it. So the direction of motion is still to the left. There's still a force of 30 newtons this way. And then there's a downward force of, let's say, 101.9. And this is still 10 kilograms. And we still have the same coefficient of kinetic friction. That's 0.2. And we still want to calculate the acceleration vector. What do you think? Is the answer here going to be different or the same? 50-50. So, okay, so think for a second, if there's no friction, if you're doing this calculation and there's no friction, do you think the answer will be the same or different for the acceleration? It would be the same if there's no friction because, you know, like I said at the beginning, if there's no friction, we would just skip this y equation and go right to the x equation so that force in the negative y direction wouldn't affect anything. We'd solve it without even seeing it. If you truly have no friction, then a vertical force pushing it into the surface doesn't change anything. Well, that's a little counterintuitive, I think, because even for us, even in low friction cases, there's some friction. When there is friction, it does matter. And the way that works is, so how is that going to change the calculation? Pushing down on the top like that, what variable is going to change? The normal force, yeah, exactly. So if this is the object, and say it's sliding this way, right now it has a very low normal force. The table doesn't have to push up very hard to keep it from sinking into the table. But if I push down on it like this, the table has to push a lot harder up to keep it from sinking into the table. And that's the N, that's the normal force. And since the friction force is just some constant times the normal force, if you increase the normal force, you increase the friction force. You know, just like this table, I could push on it, like I could get it moving without too much trouble right now, but if I put 200 pounds of weights on it, it'd be really hard for me to get it moving. And that's because the normal force would be bigger, the floor has to push harder, and because the normal force is bigger, the friction force is bigger. Okay, so here's the free body diagram now. We have a downward force of 98.1 and another downward force of 101.9. You thought I was crazy when I did that, but now you see. But those add up to 200 newtons. And then there's a force to the right of 30 newtons. And then there's a normal force of N. And then in the opposite direction of the velocity, there's a force of 0.2 times N. So now Newton's second law says 0, negative 98.1 plus 0, negative 101.9 plus 30, 0 plus 0n plus 0.2n 0 is equal to 10 times the acceleration. This can only move horizontally again, so the acceleration vector is a0. The y equation says negative 200 plus n is equal to 0. And the x equation says 30 plus 0.2 times, oh, well, let me solve this first. So n is equal to 200. And now plug that into the x equation. So we have 30 plus 0.2 times 200. Is equal to 10a. And so I guess there wasn't really any super big benefit to having that equal 200. So 30 plus 40, we get 70 is equal to 10a. So a is equal to 7 meters per second squared. Plug that variable back into the acceleration vector, and the acceleration vector is positive 7, 0 meters per second squared. That's in the positive x direction, so that's also, you could write it as a vector this direction with a magnitude of 7.0. So is this box speeding up or slowing down? Slowing down, and is it slowing down more or less than in the first case? More. That acceleration magnitude is bigger, so it's slowing down faster. And if you kept those forces going, that acceleration would stay constant, and we could actually, like calculate how long it would take for it to come to rest using the old stuff, the kinematics of a particle equations. And what you would calculate is that when you're pushing down on it, it would stop a lot sooner than it would when you're not pushing down on it. Any questions about that? Okay, so we're going to do something now. From now on, when we do problems that involve rolling or sliding, rolling and sliding problems, we're always going to, so we're going to start choosing coordinate systems now sometimes that are not the usual coordinate system. We're going to rotate them. And the way we're going to choose what the coordinate system is the y-axis will point directly out of the surface. Okay, so let me give a couple examples. So if you had something like this and you had an object sliding along this incline, you choose the y-axis pointing straight out of the surface. And then because of the rule that says coordinate systems can only be rotated, that means the x-axis has to be that way. You don't have any other choice of what direction x goes. or if the incline is like this, the y-axis points out, and so the x-axis in this case has to go that way. And we'll even do this in cases where, like, if something's sliding along a wall. You know, in that case, you'd have to have some kind of force holding it in contact with the wall. But which way would the y-axis go here? To the left. And if the y-axis points that way, which way does the x-axis have to point? Up. Good. So why would we do this? Well, first of all, you don't have to do this. But, you know, like I've said from the start of 2D, you could do any problem in any coordinate system. That's an arbitrary choice. So why would we choose this wacky coordinate system? But why? Okay, so here are the benefits that we get from it. Always, if we do this, we can always represent the acceleration vector as a0. And a can be positive or negative, but we'll always start with it written like that. And notice, if we use a normal coordinate system for this, its acceleration would be at this funny angle, you know? That would have x and y components, and we'd have to deal with x and y components. But since we have the coordinate system rotated, this thing can only slide parallel to the x-axis. So it's way easier for acceleration this way. Okay. Second, the normal force is way easier. So that means force, the normal force. The normal force is always just going to be 0, positive n. And again, if we used a normal standard coordinate system for this, the normal force would be perpendicular to that surface, so it would have x and y components, and we wouldn't know the magnitude, and so it gets messy, you know? And then the last benefit is that the force of friction is always parallel to the surface. So the force of friction is always going to be plus or minus the coefficient times the normal force in the x component, and then 0 for the y component. That's, you know, 3 good reasons to do this. There's one drawback. So I mean, obviously, like that sounds good to have these 3 benefits and then only one negative side effect of changing the coordinate system. What's the force that goes screwy now that we rotated the coordinate system? Gravity, yeah. So if your gravity is always straight down, right? And if your coordinate system is tilted, then the weight force gets more complicated. In general, we're going to have x and y components now to the weight force. Okay, so let's think about, like, if this is the incline, and let's say it makes a 20-degree angle with the horizontal. And the coordinate system has the y-axis like that and the x-axis like that. Then, just for reference, there's a horizontal and there's a vertical, okay? That's not a coordinate system, that's just a physical reference that's horizontal and vertical, okay? The coordinate system now is and let me draw onto this. Here's the weight force, right? The coordinate system we choose doesn't affect the weight of the object. It's always down at whatever. So there's mg. Now the coordinate system is like this. Where this is the positive x-axis. This is the positive y-axis. This angle is 20 degrees. This angle is 20 degrees. This angle is 20 degrees. And this angle is 20 degrees. Now, if the green is the coordinate system, in that green coordinate system, what would be the sign of the x component of the weight force? I think, so if you see it as negative, negative, then you're almost thinking about it right. You're thinking about the signs of the components of the green line in that red thing, but that's not what we have here. We have the black vector is the force, and our coordinate system is the green. And so what you have to do here is just basically like you did in all those vector practice problems. This is in the fourth quadrant. The black vector is in the fourth quadrant of the green coordinate system. And so it's going to have a positive x component and a negative y component. You'll get better at this as we do examples and stuff. But I know it's confusing at first, but just keep reminding yourself when you get frustrated that the alternative is to deal with sine and cosine in all three of these in every problem. And those are variables, so you'd have to do sine and cosine of a variable and then solve for it. It would get really messy. So this is here to help you out. So don't get frustrated. Okay? Okay, so let's do an example. In this one, so you would go from the positive x-axis all the way around to the weight force. So it would be 90, 180, 270, plus another 20, so 290. So yeah, in this one, theta would be equal to 290. Or you could think of it as negative 90 plus 20, so negative 70. That would give you the same thing. The magnitude is the weight. The magnitude is mg. So you'd multiply. So if it's 10 kilograms, the weight force magnitude would be 98.1 newtons. And you take 98.1 times cosine and sine of 290. Okay, so let's say this angle is 30 degrees. And this box has a mass of 10 kilograms. And at this instant, it's sliding down the ramp. If the coefficient of kinetic friction is 0.1, oh, I didn't talk carefully about the units of the coefficient of friction. So look at this equation that we use it for. and tell me what the units are. Where is it? Okay. So the magnitude, the force of friction magnitude is equal to the coefficient times n. So what are the units of the friction force? Newtons, it's a force. What are the frictions of the normal force? Newtons. And so what units do you multiply times newtons to get newtons? Oh, it's like a trick question, kind of. Yeah, you don't, yeah, no units. So that means that this coefficient has to be just a pure number, okay? If that was, say it had units of meters, then that would say meters times newtons is equal to this, and this would have to have units of Newton meters, and that doesn't make sense. So anyways, the coefficient of friction is just a number. And we want to calculate the acceleration vector. Okay, so the first thing is choose the coordinate system. The y-axis goes out of the surface. And so the x-axis in this case has to be that way. And then draw a free body diagram of the box. There's a downward force of 10 times 9.81, so 98.1. There's a normal force like that. Which direction does the friction force go? It goes to the right and up along the surface. So that's 0.1 n for this. And so expressing the acceleration vector, the normal force vector, the friction force vector, those are all easy now. We have that rotated coordinate system. But we have to deal with this this weight force of 98.1. So, no. So let's draw. So there's the horizontal and the vertical. And the coordinate system, the x-axis is that way. The y-axis is that way. And since if you think, I think for me, the easiest way to picture this is imagine this green thing being a solid, like what do they call that, where you're in the dark and the cold, fixing your tire wheel. Oh, I know. The tire jack, not jack, the tire iron, yeah. This thing's a tire iron, good job. So imagine the tire iron starts out aligned with the red one, okay? And then you rotate it 30 degrees like this, okay? So it's 30 degrees between this and this, between this and this, between this and this, and between this and this. So this is 30 degrees. This is 30. This is 30. And this is 30. And then the weight isn't affected by this change in coordinate system. It's still just straight down. with a magnitude of 98.1. So now what we need to do is figure out the counterclockwise angle from, let me draw the X and Y on here. So there's the X-axis, there's the Y-axis. So counterclockwise, what's the angle we have to go to get from the positive X-axis around to the weight force vector? You know, this is exactly like problems that you did in the vector practice problems. So it would be, yeah, 240. Yeah, right. So you start here. It's 90 to get there, 180 to get there, 270 to get there, and then backtrack 30. So 270 minus 30 is 240. So theta is equal to 240 degrees. And so the weight force vector, I'll call it mg vector, is equal to 98.1 times the cosine of 240, 98.1 times the sine of 240. The one for cosine is positive 49.05. Can someone calculate 98.1 times sine of 240? What is it? Negative 84.96. This is something that is easy to mess up. Why? That weight force is down. Why didn't I multiply this, the cosine and sine, by negative 98.1? A lot of people, you know, that's an easy thing to get wrong. So why is it positive instead of negative? The sine and cosine do the directions for you. You know, those negatives are just directions. And so you always multiply the magnitude, the positive magnitude of the vector, times the cosine and sine, and it gives you the sign where it needs it. When you use a standard coordinate system, you can think of it as 98.1 times cosine and sine of 270, and that just comes out on its own to be 0, negative 98.1. Yes, that's right. Yes, thank you. Yeah, I messed this up. That's right now, I think. The signs are definitely right. I think the numbers are. Yeah, that has to be right. Has to be. Yeah. No, whatever's in the calculator is what you put in. Yeah, that's right. You can always check those. Sort of a sanity check is you can tell from the quadrant what it should be. So the calculator should match up with what, you know, what quadrant it's in. Okay, so now Newton's second law. So go up to the free body diagram. We have the weight force that's now this sort of complicated thing. We have the normal force that is just always going to be 0n. We have the friction force that's only going to be an x component. In this case, is it a positive or negative x component? Positive, yep. So that's 0.1 n 0. Those are all the forces, and then those are equal to the mass times the acceleration, which also we're always going to represent the same, just a0. because it can only move along our tilted x-axis. So the y equation says negative 84.96 plus n is equal to 0. So n is equal to positive 84.96. And then plug that into the x equation, you get negative 49.0605 plus 0.1 times 84.96 is equal to 10a. So negative 49.05 plus 8 point, that rounds to 50, is equal to 10a. And so negative 40.55, right, is equal to 10a. So a is equal to negative 4.055. And then plug that back into the acceleration vector, and you get negative 4.055 for x, 0 for y, meters per second squared. Or in other words, it's in, it's pointing in the negative x direction. The negative x direction is down the ramp. So it's accelerating this way with a magnitude of 4.055 meters per second squared. So is it speeding up or slowing down? Yeah, the motion was down the ramp, so it's speeding up. In other words, the friction always works to slow it down, but in this case, gravity is pulling it down more than friction is slow. Gravity is trying to speed it up more than friction is trying to slow it down, and so it's still speeding up a little bit. So what would happen if there was no friction? Would the acceleration be a bigger negative number, a bigger number in the negative x direction, a smaller number in the x direction, or a number in the positive direction? That's right. So since it's speeding up, and all friction does is slow things down, contribute to slowing things down, it would be accelerating even more if friction wasn't there to try to slow it down. Okay. Have you ever seen Christmas Vacation? When they oil that saucer sled and he goes takes off like 1,000 miles per hour? That is not how things behave if friction goes away. That ruined the whole movie for me. That's probably enough, don't you think? Yeah. Okay. Okay, have a good weekend.